covers section 3.1. In chapter 2, we studied what's called uniform motion, where in each time interval you move the same distance. In other words, you're traveling at constant velocity. Well, not too many things actually move at constant velocity. Most things have a changing velocity. In chapter 3, we're going to study objects that have a changing velocity. This is called non-uniform motion. So let's begin with our friend, the particle model to use to describe non-uniform motion. As you'll see, basically non-uniform motion is a fancy term for meaning you're either speeding up or you're slowing down. The velocity vectors are changing. So let's see how that works. Here we have a person who's speeding up. As you can see, the distance between the dots is increasing. The time interval is the same, so they're traveling farther. Simple language. In physics language, you could say, well, these red arrows are the difference between two positions. The change in position is called displacement. So these red arrows could be thought of as displacement arrows between adjacent time intervals. But remember, velocity is displacement divided by the time interval, delta t. And the time interval is the same because that's what always happens in a particle diagram. You take equal time. So these are also velocity because that's displacement divided by the time interval is velocity. And the time interval is the same for all of them. So you could either say, look, the displacement's getting bigger, so I know they're speeding up. Or you could say the velocity is increasing and they're speeding up. Wonder what it looks like if they were to slow down. Did you see that one coming? Now as they slow down, the dots get closer together and the displacement becomes less because you're traveling slower. And velocity is displacement divided by time, and the velocity is getting slower. So it all kind of fits together. Now we meet a new term. First you met displacement. That was a vector. Velocity, that was the rate of change or displacement divided by delta t, and that was a vector. Now we meet acceleration. Acceleration is the change in velocity divided by the time interval. That's the definition you'll see in a minute mathematically of what acceleration is. And an acceleration is a vector, and we'll learn in this section how to find the direction of acceleration vectors. Here is a good figure. It kind of goes through a little bit of a complicated view, but we're going to use our knowledge of vector subtraction to find delta v if we know the initial and the final vectors. Remember, delta v is final minus initial. So if we focus on this time interval, we could say that delta v is v final minus v initial. So remember, a minus vector is the same length vector turned in the opposite direction. We're going to subtract them, so we line them up head to tail, and the resultant, or the difference between v final and v initial, is drawn from the tail of the first to the head of the last. Sure enough, there's delta v. Delta v divided by the time interval is acceleration. So in this case, the direction of acceleration points to the right. So how in general do you find the direction of acceleration? The common misconception physics students have is that positive acceleration means you're speeding up and negative acceleration means you're slowing down. That is wrong. This page, and specifically figure 4, is what you need to know. They give you 3 examples. You're either traveling to the right and speeding up, traveling to the right and slowing down, or the same thing in the opposite direction, to the left and speeding up, to the left and slowing down. And they've gone through the little exercise that we went through on the previous picture for each one of these 4 cases. Here's the takeaway. When the car's acceleration is in the same direction as the velocity, the car speeds up. Let's see if that works. This is a speeding up one, right? And the velocity points to the right, and acceleration points to the right as well. How about this one? This one's speeding up. Velocity points to the left, and acceleration points to the left. So you can't say a negative velocity is a simple negative and positive mean you're speeding up and slowing down, because look, the velocity, the acceleration vector changed directions, and in both cases we were speeding up. Now, when velocity and acceleration are in opposite direction, you slow down. So in this case, you're slowing down, velocity is to the right, and acceleration is in the opposite direction. In this case, we're going to the left and slowing down, and the acceleration vector is to the right. So put that in your notes and in your mind. When velocity and acceleration point in the same direction, you speed up in whatever direction they point. When they point in opposite directions, you slow down. You're moving in the direction of velocity, but you're slowing down. Okay, well, we did position time graphs, so now let's look at velocity time graphs, which are simply plots of the velocity versus time, such as this graph shown here. And look what we can learn from a velocity time graph if we look at the slope of a velocity time graph. Slope is rise over run, generally called m. If we were calculating it in this example, we'd have 5 meters per second squared. But look at what in this problem, the rise is a change in velocity and the run is a change in time. So now we have the slope is a change in velocity over time. Well, that is the definition of acceleration, how much you speed up in a unit of time. Let's see, here's a good one to kind of practice, see what we know. We got different velocity time graphs all shown here. And we're supposed to line up. Let's see, this one says constant eastward velocity. Well, that means you gotta be going on the east side up here. And if you have a constant velocity, that means it's not changing, which means the slope is 0 because there's no change in velocity. What do you think the acceleration is if you're moving at constant velocity? Can you tell it's 0? Because delta v is 0, so delta v over delta t will be 0 acceleration. You're not changing, speeding up or slowing down. Constant westward velocity. Well, that one's easy. It's just the one down there on the west side. Speeding up. Well, that means your velocity has to be increasing. This one goes from 0, let's say 1, 2, 3, 4. It's getting bigger. That's a speeding up curve. You might say, well, what about this one? That one's just like that. It's got a positive slope. But look, you start with a velocity in the west direction and you head towards 0. So suppose you're going 5 westward, 4 westward, 3 westward, 2 westward, 0. That's not speeding up, that's slowing down. And then after that, after coming to a stop at 0, you then increase your speed. So first you're moving towards the origin from the west, and then when you hit the origin, you kept going and moved towards the east. So that's an example of changing direction. Slowing to a stop, well, this one. It's got, say, 10 meters per second, 9 meters per second, 7 meters per second, slowing down, heading towards 0 on the velocity graph. So this one's heading towards a stop. Well, just as we talked about average and instantaneous velocity in chapter 2, now we're going to talk about average and instantaneous velocity, acceleration, excuse me. And how do you get that? Well, think of a velocity time graph. And no, this time it's not a straight line, it's changing. Well, the average acceleration is just the change in velocity divided by a time interval. So if we want to know the average acceleration between 2 and 4 seconds, we would just find the slope of the line that connects 2 and 4 seconds. The other thing that's interesting to talk about in acceleration is the units. They're a little strange. Acceleration is change in velocity over time. So velocity is meters per second divided by another second. When you put that together mathematically, you get meters per second squared. But that's an odd unit. Think of acceleration as how much your speed changes every second. Now there's also instantaneous acceleration. Instantaneous means at a given instant in time, not over a period of time or interval of time. You can find the instantaneous acceleration again from the slope of the velocity time graph, but this time not between 2 points over a time interval. This time you have to draw a tangent line on the velocity time graph at 1 point because it's 1 instant in time, and then find the slope of that tangent line. Tangent lines are a line, say at 2 seconds, we want the tangent line. You'd use a ruler to draw a line that matches the slope of the red curve best it can at 2 seconds. And then you find the slope of that line, the tangent line you've just drawn. We'll practice that. Now, mathematically, acceleration, as we've talked, is a change in velocity over time. How much are you speeding up or slowing down every instant in time, or maybe every second. So you might notice it's also very similar to the velocity. Velocity was change in displacement over time. Acceleration is the change in velocity over time. Let's have a quick look at the self-check. A VT graph shows an object's velocity over time. The rate at which, whenever you see a rate, that means divide by time. The rate at which an object's velocity changes. So what is change in velocity divide time? Well, that's acceleration. Blank acceleration is equal to the change in velocity divided by the time it takes, as in a time interval. That means it's an average acceleration. Blank means that equal displacements occur during successive time intervals. Well, that means you travel the same amount of distance every time interval. Well, if you're going the same distance in the same amount of time, that means you have, you have uniform motion. Remember we said this chapter is all about non-uniform motion when you are speeding up or slowing down. So if you have equal displacements, you have uniform motion. If a car travels 80 kilometers in a straight line for the first hour of its trip and 80 kilometers in the next hour and continues on this way, then its motion is quite uniform because it has the same displacement every time interval. I hope this screencast has helped. If you have any questions, please bring them to class.